we've been writing compounds as formulas where we've been writing things such as, for example, we've been writing CaCl2 for calcium chloride. You know what I mean? We've been writing CuCl2 for copper 2 chloride. You know, we've been writing formulas down. All right, but compounds are more than just like the name. Just like for you, you're more than just your name. You are actually a person. You are three-dimensional. You have skin. You have bones. You have shapes. You have sizes. Right? There's a lot of things that make up what your name is. Well, there are a lot of things that make up what the element is, or excuse me, the compound. Other than the elements that make them together, there's also a three-dimensional aspect to it. There is also an artistic or a visual display to it. And so the visual display of a compound is what we refer to as a Lewis structure. All right, and so what we have to do here is we need to understand how the visual goes. For example, we sort of saw this the other day when we were talking about covalent bonds. When we talked about water, we said looked like this. When we drew the atom model for water, it looked like that. That's a Lewis structure, okay? Because that's showing you, not only is it showing you how many H's are there, it's showing you how many O's are there, and it's also showing you how it's arranged. So what a formula, which is H2O, what a formula cannot tell you is the arrangement, the visual part of it. It can tell you who's in it and how many there are, but it doesn't tell you what does it look like, what is its shape. This can tell you its shape, all right, when we look at this. This is a Lewis structure. This is a chemical formula. But for you to understand how to get a Lewis structure, we have to understand a dot diagram first. And a dot diagram is simply an atom model without all the extra other stuff. It only has what we need, okay? So, Essence, was your hand up?
I was going to ask, was it two different subjects, like a dot diagram?
They're two separate things, but you need one to get you to the other. Kind of like valence electrons and oxidation numbers. They're not the same thing, but you can't get an oxidation number without a valence electron, so they kind of go together. All right? So a dot diagram. A dot diagram is a visual of the valence electrons for an element. All right? It is what I call a lazy atom model. So now we can do an atom model, and just to review that, for example, we're going to take a look at an element. Let's go to sulfur. All right, so once you have written that down, find sulfur on your periodic tables, which means for most of you, you need to take out your periodic tables. And so once you have, let's pretend that we're going to draw the atom model for sulfur. Okay, so we're going to draw the atom model the way we've done it for the past 3 weeks. Okay, the atom model for sulfur. Matter of fact, it's actually been longer than that. It's been about almost 4 weeks. So the atom model for sulfur. If I was going to draw the atom model for sulfur, the first thing I need to know is how many rings I need to draw. All right, so if I'm doing that. What I want to know is, before I go to Jacob, I want to know from Spot. How many rings do I need to draw if I'm drawing sulfur?
Three.
Try again. Just joking. You're right. All right. Okay. So there are my 3 rings for sulfur. Okay. Like I'm drawing an atom model real quick, right? How many dots would there be in the entire model? 16, right? I would put 2 in the first. Then I would put 8 in the second one. And then I would put Brooke, how many in the last one? Because she was so quick to answer for the second one, I figured she would know the third one.
Well, I would say 8, but 8 doesn't
Still.
balance it out, so 6, because you need 2 more down on.
Okay? Or yeah, okay, never mind. All right, so doesn't matter how you get there as long as you get there. So that would be the atom model. Okay? So just so we're clear, so when you guys go, for the 2 of you that will go back and reread your notes, that's the atom model. Like that's what we've always done. That is not a dot diagram. Okay? A dot diagram is much cleaner and much easier to kind of look at. All right? A dot diagram is simply this. A dot diagram says, what's my element symbol? Sulfur. S. Okay? How many valence electrons does sulfur have? 6. So then I'm going to go over here And I'm going to put 1 dot, 2 dot, 3 dot, 4, 5 dot, 6 dot, 7, no more. All right, so therefore right here, this is a dot diagram. So when I see the difference between the two, a dot diagram is simply the element symbol with the dot of the valence electrons around it. Not all the dots, just the dots in the outer ring. Because that's the only ones we care about, because the dots in the outer ring are the only ones used to form compounds with other elements. So really all I need to know is what's out here, because that's what I'm going to be using anyway. So that's a dot diagram. Everybody good? All right. So, for example, if we go over here to, let's kind of do a couple of over here. So, 1 through 20. Give me number 1 through 20. Just 1 through 20. 18. Find 18 on the periodic table and then do a dot diagram for number 18. Be ready for me to call on you on how to do it. All right. Element number 18. Where's my sheet? Here is my sheet. All right. Element number 18 is argon. So I'm going to go ahead and write AR for argon, and then I'm going to call on somebody. So I don't need you to volunteer or anything. I don't need you to say anything out loud. I just need you to be ready. Remember, we're drawing a dot diagram, okay? Which means what I'm wanting you to do is not have to draw an atom model for everything to draw a dot diagram. All right. Can say go. Number 1 through 21.
7.
7. Okay. Number 7. Wrong class. Number 7. Jacob. How many dots should I put? 8. So I'm going to go here. Argon. 1, 2, 3, 4, 5, 6, 7, 8. There's your dot diagram for argon. Okay. Now again, the whole reason what I'm saying is I don't want you to have to draw an atom model every time you need to do a dot diagram, because then you're just doing two things for one. All right. The whole point of me drawing them side by side was wanting you to see how many dots in the outside ring here. 6. How many dots did I put out here? 6. See what I'm saying? So if you know how to figure out the valence electrons, then all you got to do is just say, well, argon. Argon has 8 valence electrons. Then draw argon, put 8 dots around it, and then you're done. So you don't have to draw the atom model in order to get the dot diagram. Are we good right there? All right. So let's go with magnesium. Okay. Go ahead and do magnesium. And be ready. Because remember, I've shown you 2 ways to get valence electrons. One was using the atom model. The other one was just using the periodic table. All right, dot diagram. Did I call on spot or Tachyria? Which one did I call on already?
B.
Spot. All right, Tachyria. How many dots am I putting? 2. All right, so I'm gonna put 2 dots, 1 dot, 2 dots, and there's my dot diagram for magnesium. Okay, that's all a dot diagram is. Okay, so that's lesson on dot diagram over, unless you're still confused in how I'm getting them dot diagrams.
So it's not gonna be like no more stuff too. Like, just eat.
That's it. That's what I'm saying. It's literally just this, but more clean. Because I'm getting rid of all the extra stuff. I just need the dots on the outside and then the symbol. Boom, right there. That's a dot diagram. Okay? Any other questions about a dot diagram?
No, but is it gonna be on our test on Friday?
Am I teaching it right now?
Yes.
Is it before the test on Friday?
Yes.
Then yes. All right. All right, so let's go now, because now the whole reason we need to do the dot diagram is because for you to understand how a Lewis structure gets it visual, it makes a whole lot more sense when you have the dot diagram. All right, so what we're going to do now is get into a Lewis structure. And so a Lewis structure is a visual diagram of a compound. Okay? It includes the information that's in the formula. So it includes the element symbols. It includes how many elements there are. All right? So it is a visual, okay? So let's just say it includes the stuff in a formula. Okay? But now here's where we get into the scenario of where you need to kind of pay attention to what's going on with the whole valence electrons and whatnot. So what we're going to do here is this. We're going to do an example of a dot diagram for dihydrogen monoxide. Okay? So we're going to draw the Lewis structure for dihydrogen monoxide. Now, my suggestion always is this. For you to get the Lewis structure, it helps for you to do the dot diagrams first for what's involved. So what I say is I need to do an inventory. Okay? So in dihydrogen monoxide, that's my formula, that's my compound. Okay? But what I need to know is this. I need to know who are the elements in this compound. Who are the elements?
Hydrogen, oxygen.
Okay, so I have hydrogen and oxygen. We know that, right? Now the other part I need to know is this. How many hydrogens are there? Two. So therefore, what I'm going to do now is I'm going to go over here and put H. Then I'm going to put H. All right, how many oxygens are there? One. Okay, so now I'm going to go over here and I'm going to put the symbol for oxygen. So all I've done so far is put the symbols up there. And then what I am going to do next is do the dot diagram for each of them. So what I want you to do right now at yourself, at your own table, is go ahead and do the dot diagram for those three elements that I have up there. These three atoms, okay? I used to have index cards. Anybody got an index card? Never mind, got them. Everybody got your dot diagrams done? Okay, and let's hoping that they look like mine. If not, then you did something wrong and you might want to ask for help.
I didn't put no name.
Oh, you don't? I'm sorry. Okay. You should have the same number of marks around your element as I do. All right. So, need my tape. All right. So, right now, I've got this guy up there, okay? So, the reason why I think the dot diagram helps you in forming the Lewis structure is it helps you know, it helps the visual because it helps you to see where things should go. Like a puzzle, right? You have a puzzle, you got a shape over here, like you got the female shape over here, then you got the male shape. Then you got to figure out the male and the female have to fit in order for that piece to go and get locked in the puzzle. Well, that's the same thing we got to do here. We got to figure out where do these pieces fit, and then when we know where they fit, we begin to see the visual shape take place. So right here, remember when we did our dot diagrams here? Remember when I said that those are together, that's a pair? And that's a pair. If they're a couple and they're at the club, can this one be going looking for singles? No, right? So therefore, these right here, we should pretty much leave alone. These right here, we should pretty much leave alone. This is free to hook up with whatever it wants to hook up with. This is free to hook up with whatever it wants to hook up with, okay? And hydrogen, all it has are a bunch of singles. So they're just looking to hook up with anything, okay? Now, the whole issue here now becomes is this, though. When I see single, single, I begin to see that's where one of these things is going to go. When I see single, single, I kind of now recognize that that's where they should go. So it makes it easy for me to know where does this H need to go, and I put it in the right place. It's based on where are the single electrons, because the single electrons need to pair up, because we said that when we were doing electron configurations. So, for example, if I were to take this hydrogen right here, and it's looking for a single, what happens then is when I put this hydrogen right here, I begin to see now that I have an oxygen and I see a hydrogen. All right? If I were to draw another one, because it makes it a little bit easier for you to see, if I draw another one right here, the other hydrogen, this hydrogen now, right, with this single, when I take this one and it looks for a single electron to pair up with, it's going to come over here and it's going to pair up with this one right over here. So now when I see it, right, I begin to see that I have a shape that looks a little bit like that right there. Do we see it? Okay. Notice this. It's basically you got like a line that's been broken, right? Well, this is actually what we call a bent shape. Okay. So this, the name of that Lewis structure is called bent because the line is bent. Well, why is it bent though? It's bent because when I put my singles together, I get a shape that looks like it's bent. And so that's what we want to do. So for example, when I draw hydrogen and the oxygen, we got that shape right there, that bent shape. Well, why did it have that bent shape? It has that bent shape because when I put the singles together, that's the shape that it ends up resulting in. So that's what we have here in regards to our Lewis structure. So our Lewis structure would actually look like this. So you have this over here. That's what you have, okay? And then if I draw it over here to the side, if I put it all together, because there are two variations that they may show you of a Lewis structure. One variation looks like this. You have oxygen, 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 oxygen with a hydrogen, and here you have another with a hydrogen. So that is one Lewis structure that they could show you, where they just show you where the paired electrons are, okay? That's a Lewis structure, because that's basically I'm putting my dot diagrams and I'm putting the puzzle together. All right? That's a Lewis structure. Another Lewis structure, though, is this, where they say, where we have the single from oxygen and the single from hydrogen. Sometimes they'll represent that with a line to represent a bond. And so when they use that with a line to represent a bond, what then they would show you is something that looks like this. And so either one of those is a Lewis structure. So again, so for the two of you that may look over your notes, okay, this is a Lewis structure. For those two of you that will read your notes, this also is a Lewis structure. So they could show you the paired electrons, the ones that have paired up, or they could represent those paired electrons with a line. So anytime you see a line, that lets you know you have two electrons. All right? Because this right here, just for the sake of labeling things here, this is what we call a single bond. All right? But that's what a Lewis structure is. And again, this structure here has the shape of a bent line. That's why this shape is called bent. All right, because it's got a bent line. There are some things that have a straight line. Those things we call linear. Okay? Then there are things that have the shape of a pyramid. Those things we call pyramidal because they look like a pyramid. And so what we need to do, though, is we need to get comfortable with the dot diagrams because the dot diagrams help us see where things get laid down. And therefore, that's where we can start to see how the shape works out to play. So, can I erase my left half of the board? Because I know some of you are still writing the right half, I guess. Can I go with the left half erased? All right. Because what I want to do here is find a compound formula. All right, I got it. All right. what I want to do now is take a look at this one here. So we're going to take a look at a compound that is called, actually, let me show you, let me stay easy. So we're going to go with nitrogen trihydride. All right, so we're going nitrogen trihydride. All right, so what I want you to do is I want you to go ahead and write the formula for nitrogen trihydride. I'll give you a minute to do that one. And then once I verify that your formula is right, in case you're doubting it, then you're going to do your dot diagrams for the things that are in that formula. Now, if you've got all the confidence in the world, you can go on without waiting for me. But if you don't have that confidence in the world, then you might need to wait for me. Can I erase the right half?
Mm-hmm.
Say no if I cannot. Okie dokie.
No, I like that. I'm trying to see.
So remember, the first thing you're doing right now is you're writing the formula for nitrogen trihydride.
Is this on?
Hold on, I'm going to go over it in about 10 seconds.
Are we doing the Lewis structure too? Or wait?
Yes, we're going to do everything from the name to the formula to the dot diagram to the Lewis structure.
I'll stop with the dot now.
Okay. I mean, that's fine. You can stop wherever. All right. JD, what's the formula?
I put NH3.
You put NH3. Barrow, what'd you put?
NH3.
All right, then it must be right. So we're going to go NH3. There's your formula. All right. So then again, that means I'm going to have how many dot diagrams that I got to do?
2.
Try again.
4.
4. Okay, because remember, I got to do each element, but also each number of the same element that I have. So again, how many nitrogens do I have? 1. So I'm going to put N. How many hydrogens do I have?
3.
So I'm going to put H, 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 right? Because remember, those are the pieces to the puzzle. Until I lay out the puzzle, it's hard for me to see where things go. All right, I can't just take a piece of the puzzle and then take another one and just say they're going to go together. No, you got to see how everything lays out. You got to see the whole design of it all. So nitrogen, when you do the dot diagram, looks like this. Hydrogen, hydrogen, hydrogen. Right? And these are the ones that are always the ones that make me smile, the ones that make me happy. Because when I look at the nitrogen dot diagram, I see that nitrogen has how many single electrons? 3. And I have how many hydrogens? 3. And each hydrogen has how many single electrons? 1. So I already know all the single ladies and all the single men, they can get together, right? Because that makes it easy. What makes it a little bit more difficult is when it's not as obvious, okay? But right now, here's what I know. I know that this one says, I'm going right here. This one says, I'm going right here. And this one says, I'm going right there. Like, that's how I can see the puzzle being laid down together. And so when I do that, I'm going to get nitrogen with its 3 single electrons, and then I'm going to get hydrogen. Like if I'm going to draw it exactly like I have up here, it would be hydrogen right here with its pair, hydrogen right here with its pair, and then hydrogen right here with its pair. Like that's how that shape is going to look. Okay, that's how that shape is going to look. And right now, if you look at this right here, like if I drew the other Lewis structure, it would look like this. Okay, and when you look at that Lewis structure, that looks like a what? Like a T. And guess what? In the two-dimensional name, so now we're going to get into something a little bit else here. In the two-dimensional name, this is called T-shaped. Okay? The three-dimensional name is not called T-shaped. This is called pyramidal. Okay? This is called pyramidal. So here's where your life gets a little bit chaotic. Okay? But I'm going to kind of emphasize something, which is the fact that you're not honors means that I'm not going to go crazy on you, but I do need you to be aware of stuff. Which means if your test on Friday is 50 questions, I may ask you one question where you have to know the difference between a two-dimensional name and a three-dimensional name, as opposed to 10, if you were in my honors class. All right, because I do need you to be aware that sometimes the two-dimensional name does not match up with the three-dimensional name. All right, and the reason why is really kind of simple. All right, I'm going to take this thing right here, which is supposed to represent an atom model, which I'm going to try to make it look like an actual atom model. And I'm going to actually do the atom model for nitrogen trihydride. And if I do it right, this should make sense. But if I don't, then it won't make sense. And I don't think I did. Apparently I have the wrong ball here, but I can get you close enough. Okay, so now, if I take, what we're looking at here is nitrogen trihydride, okay? Two-dimensional name T-shape, right? So again, the issue here that you look at is this. Imagine if we were to look at this directly from the top view, okay? If we look at it directly from the top view, what you would see is you would see the black ball with a stick to the side, a stick to the side, and a stick going down. That's what you would see, right? Hence, looks like it's two-dimensional. I mean, it looks like a T-shape, right? But that's if I look at it as if it's flat. When I take this away, though, and you look at it now, you actually see that it's got these little three legs that if I set them right here, they can sit up there. So when I look at it on that angle right there, it looks like I have this with a leg that's coming out, a leg that's coming out, and a leg that's behind there that's sticking out, like a spaceship, right? So you can see, when I look at it flat, it looks T-shaped, but when I look at it three-dimensional, it looks like a little pyramid. Okay? That's why it's called pyramidal, the 3D name. The 2D name is called T-shaped. Because if I look at it on a flat surface, it looks one way. But if I look at it in reality, this is the reality right here. All right? That looks like a shape of a pyramid. All right? And so that's why it's called pyramidal. Does everybody get that? So my main idea, the main point I'm trying to get across to you right now is this, and I don't even know if I caught that on video. I think I did. All right, is that the 2D name and the 3D name can be different because the two-dimensional shape that you see sometimes doesn't match the three-dimensional shape that you see. The reality sometimes is not what's on paper. The reality is sometimes what's in front of your own face, and that's what we're trying to get you to understand. Are we good? All right. So now let me give you another guy, because let me give you another fancy word. We're going to look at methane. Okay, methane is carbon tetrahydride. All right, so notice I'm still staying with things that are easy. Methane is carbon tetrahydride. So please go ahead and write the formula for carbon tetrahydride. All right. The first thing you're doing is writing the formula. Elijah, formula.
CH5.
CH5. Catch your part, you agree or disagree?
I disagree because CH4.
You go CH4. All right. Essence, which one you going with?
I don't know if the oxidation is
I'll come back to you. Which one are you going with, Barnes?
I go with Logan.
You're going with Logan? All right. Tetra means 4, so it is CH4 essence. Because it's a non-metal, I could give 2 poops about the oxidation number. Because remember, when I'm giving you prefixes, right, oxidation number is not needed. It's needed when you have a metal to a non-metal. Okay? So, this is going to be CH4. Kalijah, you saw your mistake? All right, so I got C, H, 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 dot, 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 dot. How many dots around carbon? 4. What do I see? How many single ladies?
4.
I got 4 single ladies, right? So again, right here, you would get a shape that looks like this. Right? You would get that. But that is the 2-dimensional shape. All right? The 2-dimensional shape for that is not match up to 3-dimensional shape. Where did my spaceship go? Here it goes. All right? My 3-dimensional shape, which I lost a ball. That's no pun intended. But if I take that nitrogen trihydride and I stick another probe going up top, that's what the shape for methane looks like. However, though, again, if I take it and look at it in a particular type of way, being this way right here, if I kind of get it to a certain angle, you can see the cross, the line going down. You can see the line going across. But that's if it's flat. But this is not, reality is not 2-dimensional. Reality is 3-dimensional. So when I take this right here, we have basically my pyramid with the stick going up. Okay? That has got a ridiculous sounding name. Okay? The 3D name for this right here is called a tetrahedron. Okay? A tetrahedron. Tetra because it means what? 4. That's why I got 4 sticks coming out of that thing. All right, so I can kind of see why now it's a tetra, right? But the hedron now, when we get into geometry names and shapes and all that, right? The whole point here is it's not a flat plus symbol sign. It is a pyramid with a stick coming up across the top. It's like a space probe with an antenna and 3 legs sticking out the bottom. All right?
You said that we're going to have to know the 3D names coming to the front.
You need to, I need you to be aware of some of the 3D names and the ones that I'm throwing on the board right now. All right? Are we good with that one? So I gave you tetrahedron, I've given you pyramidal, I've given you bent, right? The only one I haven't given you right now is linear. And linear, I'm going to give you a weirdo so that you can kind of see how linear works. Because you can get linear with 3 elements. Like, for example, what was the first one we drew? What was the first one we drew?
H2O.
H2O. How many atoms? 3. How many elements?
3.
2 elements, 3 atoms. Okay, this is just so we understand the difference in the wording now. 2 elements, H and O, 3 atoms, because there were 2 H's and 1 O. What was the next one we drew? Nitrogen trihydride, right? How many elements?
4. Wait, 2.
2. How many atoms? 4. So notice, when I did water, 3 atoms, bent. When we did nitrogen trihydride, 4 atoms, pyramidal. When we drew methane, right, carbon tetrahydride, how many atoms? 5 atoms and tetrahedron, right? Now, we're going to do another one, which is CO2. Okay, CO2. How many atoms do you got? 3. 2 elements, 3 atoms, right? 3 atoms. But if you're thinking this is going to be bent, then you're about to be bent out of shape. All right, because it's not. So what we need to do is we need to go ahead and we're going to draw our dot diagrams for carbon dioxide. So we got carbon and we have 2 oxygens. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, I'm going to draw me another flashcard here so it's easier for us to see what's going on. All right, so here's one of my oxygens right here, correct? Here's one of my oxygens. Okay, 2 dots, 2 dots, 1 dot, 1 dot, right? Now, the whole issue here the thing that's harder for you to see, because we're used to singles being with singles, right? But now this has got 2 singles, and this has got 2 singles. So the way this lays out is this. When I take this around and I reposition it, I can position this so that that single will go with that single, and this single will go with that single. Do you see that? So when I do that, what happens is I'm going to now get, so if I'm going to just redraw this over here, carbon, 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 carbon. I'm going to draw my oxygens in red. I'm going to get my oxygen over here that had its 6 dots right there. That means the other carbon is going to go, the other oxygen, excuse me, is going to go right here so that they paired up, they paired up, they paired up, they paired up. All right? And when they pair up, when we look at it this way, we see that we have, like that's kind of what we see going on there. Like if I was going to literally transpose what we see here into the bar representation of it, I have that right there, then I have that right there. It's the same thing. This time, instead of putting dots, I put lines to represent the dots, right? How many dots do I have right here? 4, right? Remember I said one line represents how many dots? 2. So that's why I have 2 lines. Okay? This right here, that's called a double bond. Okay? That's called a double bond. And so if I were to simply take that right there, right, how would you describe that structure? Straight. Okay? The line, straight line, correct? Which is why this right here, 2D name and 3D name, are both going to be linear. So here the 2D name and the 3D name match. But it's a straight line. I mean, it looks like a line. That's why it's called linear. What's the first 4 letters in the word linear? Line. Okay? So you really can't get it mixed up unless you just really aren't paying attention to what you're doing. So that is your dot diagram. That is your Lewis structure. And that is your introduction into the 3D model stuff about it. All right? Without getting too much into the 3D model, because the 3D model stuff can be a little confusing. So I really just introduced the tip of the iceberg and not the bottom of the iceberg. Any questions about that right there? Uh-oh, got my spaceship. That concludes the recording of this video.